Hello, this video we're looking at a method that we have for integration called the substitution rule. So this is a very challenging rule. We're not going to rush it, but let's dive into it here. Oops. There we go. So the idea with this, the substitution rule, it's the first of, like I said, more complicated rules that we'll explore for finding antiderivatives and computing indefinite integrals. So far we basically just have our kind of standard basic rules that we had for differentiation reversed. So you had a rule, the derivative of tangent is secant squared, so that means an antiderivative of secant squared is tangent. So there's very limited with what we can handle, more than what we would be able to do just using the definition, but it's still very limited. So this is a technique that's going to kind of open up some more options, more functions that we can integrate. So the idea here, one of the things to note is that we want to remember this is the inverse process of differentiation, substitution rule for integrals. Or as a process of integration is the inverse of the inverse process of the chain rule, which is for differentiation. So one of the things you can do if you're trying to find an antiderivative, you can always check your work by differentiating that result and seeing if you end up with the original function. If you have to use a substitution rule, when you check your work with the differentiation, you will use the chain rule. So what are we trying to do here? The idea is that we want to rewrite the given integral in terms of a different variable, with the goal being that the new integral is easier to evaluate in terms of the new variable. Easier in the sense of we have a rule for it. So really, we're not changing it in a meaningful way. We're just kind of disguising it, making it look different, so we can use some of the rules that we know. Okay, so here's a first example. Suppose we're trying to integrate this guy here. The first thing we want to think about is, do we have a rule in place already? Now, suppose that it was just 2 over 1 plus x squared. Then we'd use arctangent. We know that antiderivative of 1 over 1 plus x squared is arctangent of x, but it's not quite what we have, so a little bit different there. Now, kind of what's given me the biggest issues I might think at first is that denominator. And so that's going to give me the idea to use that as my new variable, my rule from a new variable u. So there's very much an art to this process. There's no sets, step 1, step 2, step 3. But you get the feel for it with practice. So kind of look for things that are problematic, but at the same time you got to balance it out a little bit in the sense we'll see in just a second. Okay, so to evaluate the integral, we need to, everything to be in terms of the new variable, which would be u. Sometimes people call this u substitution because you use u a lot. And the thing I want to note is that if we use this substitution, remember I still have this dx floating around here, but differentiating both sides. So if you look back to what we did with differentials early on, it's going to look very familiar. Du, it's going to be 2x dx. And so in place of du, we're going to put, in place of 2x dx, we're going to put du. So let me get that part in red, maybe. That's now going to be du, and the 1 plus x squared is just u. But the whole point is, here's the old one that we didn't know the rule for. Here's a new one. It really is the same, but it looks different with that new variable name. We've got a rule for that. Antiderivative is natural log of the absolute value of u. And then back in terms of the original variable, we have our result. So the indefinite integral of 2x over 1 plus x squared dx is natural log of absolute value of 1 plus x squared plus c. A little bit more formally, it looks like this. If u is g of x, and that's a differentiable function, is range. This part with the range, it's part of what needs to work in the background, but it pretty much always does for us, so you won't probably remember it too often, and that's okay. But if it's continuous on an interval, then you've got the following here. So the idea is, here's your input variable, or your input function, kind of as a composition. Now that's what you're going to call u. And then for this part of it, du is g prime of x dx. So that's what you get right here. So just remember, you're going to substitute the u's everywhere you had a gx, whether it's 1 plus x squared or whatever it might be. But you also need to substitute for that as well, and that's something that people do forget about. Okay. If we're going to work with definite integrals, the process is the same, only now we have to be careful about the limits of integration. So these need to be in terms of the new variable. So if you had a definite integral where in the original variable you had a and b for the lower and upper limits of integration, and you use u equals g of x, then the new limits will be g of a and g of b, corresponding to a and b in the original. So for example, if this was the one we had before, if we cover up, we had that indefinite integral before. So if I go from 0 to 2, I'm using this for my substitution just as before. So this part is as before. And the way we're getting these, the 5, comes from, well, it's figuring out what does u equal when x equals 2. 1 plus 2 squared is 5. The 1 is about from here. So again, what does u equal when x equals, in this case, 0? When x is 0, u is 1. When x is 2, u is 5. And so we end up with this guy. So the anti-differentiation part's the same, just got to be careful with the limits. Some folks will not change these limits and they'll undo, they'll back substitute at the end. That's kind of bad form because this really is supposed to mean something, that equal sign there. When you're doing scratch work, sometimes you do things like that, but I encourage you to get in the habit of being consistent and being correct with the notation. Alright, so like I said, for indefinite integrals, that last step is going to be to back substitute. You want to put it in terms of the original variable. But for definite integrals, what's kind of cool about it is you don't have to put it back in terms of the original variable. Once you get, once you figure this out, this guy is in the past. Nothing to do with it anymore. Right? You're only concerned with this. So once you have everything in terms of the new variable, just compute the final answer. You don't have to do any back substitution. A couple other quick notes. You mentioned some things with symmetry. It doesn't come up too often, but it's a quick thing to mention, and it's every once in a while it's useful. Having to do with some symmetry of both the interval that you're integrating over and the integrand, which is the function. So if you're suppose that you've got a function f that's continuous on negative a to a. So if you like, this is centered at the origin. Or maybe let me just say centered at 0. If f is even, remember the way we check for that is f of negative x equals f of x. So examples, f of x equals x squared, f of x equals cosine x, things like that. Then definite integral from negative a to a of f of x is just twice the integral from 0 to a. And what you can be thinking about here is for an even function, you've got a symmetry about the y-axis. So if you're going from whatever this is to here, this part is just the same on the other side of the axis. So you could just double one of them. That's what that's saying. Now, if f is odd, so if example would be things like y equals, or f of x equals, I don't know, x cubed, f of x equals sine of x, those are some standard ones. So on. And here's the way you check that. F of negative x equals negative f of x, then this definite integral is 0. That's actually pretty nice. If you think about what's going on here, you've got a symmetry not across an axis, but about the origin. So you'd have something like, maybe something like that. It's supposed to be symmetric, where if I rotate it around 180 degrees, it looks like exactly the same thing. And so if I was going from, let's say, negative a to a, whatever I have here is the negative of it is balanced out there, so the overall effect is going to be 0. But very specifically from negative a to a. So that's kind of a useful result. Well, when it comes up, it's really useful, but in reality, it doesn't come up too often. So those are our two symmetry results. Just kind of a quick final thought here. This rule is a difficult procedure. It's the most difficult thing we've seen so far, certainly for the integration methods. And then part of its difficulty is that it doesn't have an explicit set of steps. There's not a step 1, step 2, step 3 every single time. There's a general idea, but it's something that you get better at, the feeling for what's going to work, the more practice you have. And that's what I'm saying here. So with practice, you'll get a good intuition for finding good choices for substitutions. When you first start this, you might get it to work on your third attempt, defining u equals whatever. But with practice with these, you'll find that pretty quickly you'll be making the right choice on the first time through.